In this video, we are going to be taking a look at KFold cross-validation for classification. We'll examine a bivariate dataset with 3 classes. Each class has a different number of data points. We'll illustrate this cross-validation procedure with 5-fold cross-validation, which involves dividing the dataset into 5 equally sized folds which are chosen randomly. Each fold will contain the same class proportions as the entire dataset and will be used as test data only once. So how does this play out? We first select one of the folds to be our test data, and the remaining folds are going to be our training data. In this case, fold 1 is test data, folds 2, 3, 4, and 5 are training data used to construct a classifier. We repeat this exercise with folds 1, 3, 4, and 5 being training data and fold 2 being test data. Repeat this one more time with folds 1, 2, 4, and 5 being training data and fold 3 being test data. Repeat this again with fold 4 being test data. And finally, we have fold 5, which is going to be our test data, and the remaining folds, which are folds 1, 2, 3, and 4, comprising 80% of the data being our training data. It's important to note that because we're doing this 5 times, we will be constructing the same classifier 5 different times. This involves 5 different model fits. Let's see how this plays out. So we have our entire data set broken up into 5 folds. We fit a classifier to our training data shown in the panel on the left. So when this classifier is constructed, we now need to evaluate how well this classifier is going to do when applied to previously unseen test data. In this specific example, with fold 1 being our test data, we get 100% accuracy and no misclassification as seen in the confusion matrix on the right. We then repeat this exercise, but this time around fold 2 is our test data, folds 1, 3, 4, and 5 are our training data. In this case, we can plot the training data and we can fit the same classifier to this training data. In this case, it's a logistic regression. And then we examine how well this classifier does on the previously unseen test data. Again, in this specific case, we get accuracy against the test data of 100% and no misclassification as seen with the confusion matrix on the right. We then repeat the same procedure, this time with fold 3 being our test data and the remaining folds 1, 2, 4, and 5 being our training data. We fit another logistic regression model to our training data, and the fits are going to be slightly different because each time we are using a different fold, our training data are going to be slightly different, and so the decision boundaries will be slightly different. We then examine the performance of this model against test data contained in fold 3 and keep that aside. We repeat this entire exercise, but this time with fold 4 being our test data and folds 1, 2, 3, and 5 being our training data. We again reconstruct the classifier with this new training data. and evaluate the classifier against the test data from fold 4. And again, in this specific case, we can see that the classifier has 100% accuracy. So far, we've gone through 4 model fits. For the final model fit, we have fold 5 being our test data, and the remaining folds 1, 2, 3, and 4 being our training data. Because this is a bivariate example, we can plot the training data and fit a classifier to it. And then we can evaluate this classifier against the test data. As you can see through all of these 5 different folds, 5 different model fits, the decision boundaries did not change all that much. What that's essentially telling us is that this model is relatively insensitive to the choice of training and test data, and so can generalize very well to new data. Another way to say the same thing is to look at the performance of the model when testing it against fold 1, 2, 3, 4, and 5. In this specific synthetic example, they all have 100% accuracy, and this is a good way of viewing the results. We want high accuracies, but at the same time, we also want minimal variability across testing over multiple folds. If there's minimum variability, it indicates that the model is fairly robust and can generalize well to new data. So just to recap, we went through a 5-fold cross-validation procedure. In general, we tend to use 5 or 10-fold cross-validation. It's important to remember that this can be computationally expensive because in this specific case, we only used one single model, which was logistic regression model for constructing a classifier. In general, you're going to be evaluating 7 or 8 or 9 or many more models. And when you do that, it's important to remember that with 10-fold cross-validation, it's going to involve 10 model fits of one specific model, then another 10 model fits of a second model, then another 10 model fits of the third model and the fourth model, and so on and so forth. So it can become computationally expensive, but it's a very popular approach to testing your models and validating your models because you're collecting a diversity of training data and test data. It also indicates model robustness and its ability to generalize to new data. The other thing that's important is that not only do you get an indication of the model performance across each fold, you also get the variability of the model performance across each of the folds, whether it be 5-fold or 10-fold cross-validation. And this variability should be as small as possible. It should be as small as possible because you do not want your model performance or your model to be sensitive to the choice of training or test data. If it's not sensitive to the choice of training or test data, then it can be said that the model will generalize well to new data.